Welcome! Today, we'll be tackling an exciting problem from LeetCode, problem number 1787, make the XOR of all segments equal to 0. This problem combines concepts like XOR operations and segment manipulation, and we'll explore strategies to solve it efficiently. Let's dive in. The goal of this problem is to divide an integer array nums into exactly k non-empty segments and then calculate the XOR of all elements within each segment. Once you have these k XOR results, the task is to ensure that the XOR of all these results equals 0. To achieve this, you are allowed to modify the elements of the array. Specifically, in one operation, you can replace any element in the array with any integer of your choice. The challenge is to determine the minimum number of such modifications required to satisfy the condition. The input to the problem includes the array nums, which contains n integers, and the integer k, which specifies the number of segments. The output should be a single integer representing the minimum number of modifications needed. For example, consider the input array nums equals 1, 2, 0, 3, 0, and k equals 3. Here, we must divide the array into 3 segments. One such division is 1, 2, 0, 3, and 0. Next, we calculate the XOR of each segment. For the first segment, 1, 2, the XOR is 1 XOR 2, which equals 3. For the second segment, 0, 3, the XOR is 0 XOR 3, which also equals 3. For the third segment, 0, the XOR is simply 0. Now, the XOR of these segment results is 3 XOR 3 XOR 0, which equals 0. This satisfies the condition. To achieve this valid division, we modify the array by replacing certain elements. Let's see how the modifications are carried out. In this case, we replace the first 0 in the array with 1, keeping the segment 1, 2 unchanged. Next, we replace the second 0 with 3, which ensures that the segment 0, 3 remains valid. No changes are needed for the third segment, 0. In total, 3 modifications are made to the array. Therefore, the minimum number of modifications required to achieve the condition is 3. Now let's look at another example to further clarify the problem. Consider the input nums equals 1, 2, 4, 3, and k equals 2. Here, we divide the array into 2 segments, 1, 2, and 4, 3. For the first segment, 1, 2, the XOR is 1 XOR 2, which equals 3. For the second segment, 4, 3, the XOR is 4 XOR 3, which equals 7. Now, the XOR of these segment results is 3 XOR 7, which equals 4. Since this is not 0, we need to modify the array. To satisfy the condition, we replace the value 4 in the second segment with 3, resulting in the segment 3, 3. This ensures that the XOR of the second segment is now 3 XOR 3, which equals 0. With this change, the XOR of both segments becomes 0, and the total number of modifications is 1. The problem also includes several constraints and edge cases to consider. The size of the array nums ranges from 1 to 200, and the elements in the array are between 0 and 2*10^1. Additionally, the value of k is always between 1 and the length of the array. For edge cases, if the array has a single element and k equals 1, the XOR is already 0, so no modifications are needed. If all elements in the array are zeros and k divides the array evenly, the XOR of all segments will already satisfy the condition. On the other hand, when elements have values close to the maximum, such as 2*10^1, the implementation must handle large XOR calculations efficiently. These constraints and examples help clarify the problem requirements and ensure the solution is robust. To tackle problem number 1787, the goal is to ensure that dividing the array nums into exactly k segments results in the XOR of each segment being 0, while minimizing the number of changes made to the array. One straightforward idea is the brute force approach. Here, we generate every possible way to divide the array into k segments, calculate the XOR for each segment, and modify elements as needed to make the XOR 0. However, this approach involves exploring an exponential number of segmentations, making it computationally impractical for larger inputs. A more efficient method is the optimized dynamic programming approach. The idea here is to break the problem into smaller subproblems, where we iteratively compute the minimum changes required to achieve specific XOR values for each segment. This allows us to systematically build our solution using a DP table, significantly reducing the computational complexity compared to brute force methods. Now, let's break down the dynamic programming approach further. First, we make some critical observations. If the XOR of a segment is 0, the elements within that segment can be adjusted to achieve this with the minimum number of changes. This reframes the problem as finding the minimum cost to ensure all K segments have an XOR of 0. To implement this, we define a DP table DP, I, X, where I represents the segment number, and X represents the XOR value for that segment. The transitions involve iterating over each element in the array and all possible XOR values, updating the DP table by considering whether the element is kept as is or altered to reach the target XOR. The base case is set such that DP 0x represents the minimum changes needed to make the XOR of the first segment equal to X. Finally, the solution is found in DP K1 0, which gives the minimum changes required to make all K segments have an XOR of 0. This approach has a time complexity of approximately O, K*M*N, where M is the range of possible XOR values, and N is the size of the array. This is a significant improvement over the brute force method, making it computationally feasible for larger inputs. Other approaches can also be considered, though they come with notable limitations. A greedy algorithm might attempt to minimize changes for each segment individually, but this often fails to achieve a globally optimal solution since it doesn't account for the cumulative effect of decisions across all segments. Another alternative is bit masking combined with dynamic programming. Here, bit masking can represent segments and reduce the state space, but the approach becomes impractical for larger values of K due to its exponential growth in complexity. Ultimately, the optimized dynamic programming approach strikes the best balance between efficiency and correctness. By leveraging a DP table, it systematically explores all possible segmentations and XOR values to guarantee the optimal solution. Unlike brute force, it avoids exponential growth, and unlike greedy methods, it ensures global correctness. While bit masking may be useful for small K, the optimized DP approach is the most scalable and reliable solution for this problem. It is therefore the chosen strategy, offering the best trade-off between correctness, efficiency, and practicality. In this problem, we aim to minimize the number of changes needed in an array so that dividing it into K segments results in the XOR of all elements in each segment being 0. To achieve this, the first step is understanding the XOR property. When the XOR of a segment equals 0, it means the cumulative XOR of all elements in that segment is balanced. Our objective is to ensure this property is met for all K segments by making minimal changes to the elements in the array. To solve this efficiently, we use dynamic programming. Here, we define DP, I, X, as the minimum number of changes required to make the XOR of the first I elements, divided into K segments, such that the XOR of the current segment equals X. We start with the base case where no elements mean no changes are needed, so DP 0, 0 equals 0. From here, we build the solution iteratively. Now, to fill the DP table, we iterate over the array and analyze each segment. For each segment, we explore which numbers can be modified to achieve the desired XOR value. This involves using a nested loop to iterate over all potential XOR values, which range from 0 to 1023 due to the problem constraints. The key transition step is calculating DP, I, X. For a given segment, we consider all possible XOR values from the previous segment, denoted as prev_x. We then determine if modifying the current value in the array to achieve the new XOR value x is possible and at what cost. The cost is defined as 1 if a change is necessary, or 0 if no modification is needed. By evaluating the cost across all transitions, we update DP, I, X, with the minimum cost. To optimize this process, we leverage frequency tables. These tables count how many numbers in the array can produce a specific XOR value, allowing us to directly access transformation costs instead of recalculating them repeatedly. After processing all elements in the array, the final result is found in DP, n0, where n is the length of the array and 0 represents the target XOR value for each segment. This value gives the minimum number of changes required to achieve the desired segmentation. There are several key insights here. First, the reversible nature of the XOR operation ensures efficient computation of transitions between segments. Second, the dynamic programming formulation breaks the problem into smaller subproblems, allowing us to minimize changes incrementally. Lastly, the use of frequency tables drastically reduces redundant calculations by pre-computing the cost of transforming numbers to specific XOR values. Together, these strategies provide a robust and efficient way to solve the problem. To implement the solution, we use two primary data structures. The first is a DP table, a 2D array where each entry represents the minimum cost for a given segment in XOR value. Its size is proportional to k times 2 caret 10 since XOR values range from 0 to 1023. The second is a frequency table, implemented as a dictionary, which maps XOR values to the count of numbers in the array that produce those values. This structure helps optimize the transformation cost calculations. In terms of complexity, the time complexity is O, n times k times 2 to the power of 10, where n is the length of the array. This stems from iterating through the array, segments, and possible XOR values. The space complexity is O, k asterisk 2 to the power of 10, for the DP table and O, n, for the frequency table. When considering edge cases, we must account for scenarios like arrays too small to form k segments, which should return -1. Similarly, uniform arrays require minimal changes, and large XOR values are efficiently handled within the bounded range of 0 to 1023. These considerations ensure the algorithm remains robust and efficient under various conditions. Here, we start by importing the necessary modules. The counter class from the collections module helps us efficiently count the frequency of numbers, and INF from the math module represents an infinitely large value that we'll use in our dynamic programming setup. Then, we define the solution class and its min_changes method, which takes the input list nums and an integer k. The variable n holds the length of the input list, and max_XOR is set to 2 to the power of 10, which is 1024. This represents the maximum possible XOR value since the problem states that numbers in nums will be less than 2 to the power of 10. Next, we divide the elements of nums into k groups based on their indices modulo k. For this, we initialize a list of counter objects, one for each group. Then, we iterate through nums, calculating the modulo of each index with k, and use this to increment the count of each number in the corresponding group. This allows us to efficiently store the frequency of each number within its respective group. After that, we set up the dynamic programming array DP, which has a size of max_XOR and is initialized to infinity, except for DP, 0, which is set to 0. This setup will help us track the minimum number of changes required to achieve any XOR value. Now, for each group of numbers, we initialize a new dynamic programming array new_DP, also filled with infinity. The total_count variable calculates the total number of elements in the current group. For each possible XOR value x, we iterate through the keys in the frequency counter of the current group. The goal is to update new_DP, x, with the minimum value between its current value and the result of the previous XOR computation, adjusted by the cost of changing numbers outside the current key. This ensures that we are considering all possible ways of achieving the desired XOR value while minimizing the number of changes. Finally, after processing all groups, we return DP, 0. This represents the minimum number of changes required to make the XOR of all segments equal to 0. The reason we focus on DP, 0, is that a 0 XOR value across all segments satisfies the problem's requirement. By systematically iterating through each group and computing the optimal values using dynamic programming, we ensure that we explore all possible combinations to achieve the desired result efficiently. Let's continue. In this problem, we need to make the XOR of all k-length segments of an array equal to 0 while minimizing the number of changes to the array. The segments are formed by grouping elements spaced k apart. To solve this, we use dynamic programming combined with frequency analysis. For example, when nums is 1, 2, 0, 3, 0, and k is 1, every element is part of the same group since k equals 1. First, we calculate the frequency of each number in this group, resulting in group 0 with frequencies 1 appears once, 2 appears once, 0 appears twice, and 3 appears once. Next, we initialize a dynamic programming array to track the minimum changes needed to achieve any XOR value from 0 to 1023. Initially, the cost for XOR equals 0 is set to 0, and all others are set to infinity. Finally, we update this DP array for group 0 by iterating over all possible XOR values and calculating the minimum changes required for each key in the group. For each potential XOR value, we calculate the cost of including a key from the group. For instance, when x is 0 and the key is 1, we update the DP array by considering the cost of modifying elements in the group to match the required XOR. Specifically, the new DP value for XOR equals 0 is updated based on the current DP value for XOR equals 1 and the number of changes needed. This calculation is repeated for all XOR values and keys, ensuring that we always track the minimum number of changes. After processing the group, DP0 gives the minimum changes needed to make the XOR of all segments equal to 0. In this example, the result is DP0 equals 3. Moving to the next example, when nums is 3, 4, 5, 2, 1, and k is 2, we first group the numbers by their indices modulo k. Group 0 contains elements at indices 0, 2, and 4, resulting in frequencies of 3, 5, and 1. Group 1 contains elements at indices 1 and 3, with frequencies of 4 and 2. We then initialize the DP array as before, with DP0 set to 0 and all others to infinity. To update the DP array for this example, we process each group separately. For group 0, which has keys 3, 5, and 1, we iterate through all XOR values, calculating the minimum changes needed to match each target XOR. For instance, for x equals 0 and key equals 3, we update the DP value for XOR equals 0 based on the current DP value for XOR equals 3 and the cost of modifying elements in the group. Similarly, for group 1, we process the keys 4 and 2 in the same manner. After updating the DP array for both groups, we determine that DP0 equals 1, meaning only one change is needed to make the XOR of all segments equal to 0. Now, in the final example, when nums is 0, 1, 2, 3, 4, and k is 3, the numbers are divided into three groups based on their indices modulo k. Group 0 contains 0 and 3, group 1 contains 1 and 4, and group 2 contains 2. The frequencies for each group are calculated accordingly. Once the groups are formed, we initialize the DP array as before, with DP0 set to 0 and all other values set to infinity. Then, for each group, we update the DP array by iterating over all XOR values and minimizing the cost for each target XOR. This involves considering the current DP values and the frequency of keys within the group. After processing all groups, DP0 holds the minimum number of changes required to make the XOR of all segments equal to 0. In this example, the result is DP0 equals 2. This solution highlights some key insights. By grouping elements based on indices modulo k, we efficiently break the problem into smaller subproblems. The dynamic programming approach ensures we minimize the cost at each step, while the use of frequency counts allows us to reduce the computational effort compared to brute forcing all possibilities. Together, these optimizations make the solution both time and space efficient. In analyzing the time complexity of our solution, the first step is to compute the frequency of each number in the array nums by dividing the array into k groups based on their indices modulo k. This ensures that we can group numbers effectively for further computation. Since we are iterating through the array of size n once, this step takes n time. Next, we initialize a dynamic programming array, dp, which has a size equal to max_XOR, where max_XOR is fixed at 1024 because we are working with XOR values that can range from 0 to 2 to the power of 10. This initialization is independent of the input size, so it takes constant time, making it max_XOR. Together, these two steps set the foundation for the overall time complexity of the algorithm. The next part of the time complexity analysis focuses on the dynamic programming transitions. For each of the k groups, we calculate new DP values based on the frequency data of the current group. This involves iterating over all possible XOR values, from 0 to max_XOR 1, and for each XOR value, iterating through all unique keys in the group's frequency counter. If we denote the number of unique keys in the frequency counter as m, the inner loop requires m operations. Over all XOR values, this becomes max_XOR *m per group, and across k groups, the total time is k max_XOR *m. In the worst case, where all numbers in a group are distinct, m can be as large as n/k. Substituting this into the equation, the time complexity becomes O, n plus n asterisk max underscore XOR, as the k terms cancel out. Given that max underscore XOR is a constant value of 1024, the overall time complexity simplifies to O, n, which is linear in the size of the input array. Now, let's consider the space complexity of the solution. First, we have the frequent array, which stores frequency counters for all k groups. Each frequency counter can store up to n/k unique keys in the worst case, resulting in a total space requirement of O, k asterisk n/k, which simplifies to O, n. Next, we use two dynamic programming arrays, dp and new_dp, each of size max underscore XOR. This contributes an additional O, max underscore XOR, space. Combining these, the total space complexity is O, n, plus O, max underscore XOR. Since max underscore XOR is constant at 1024, the dominant term is O, n, making the space complexity linear in terms of the input size. The use of these efficient data structures ensures that the memory footprint of the algorithm remains manageable, even for large inputs. To better understand the efficiency of our solution, let's compare it with a brute force approach. In a naive brute force method, we would need to try all possible combinations of changes to the array nums to make the XOR of all segments equal to 0. This involves iterating through all subsets of nums, resulting in a time complexity of O, 2 to the power of n, which grows exponentially with the size of the input. In contrast, our optimized dynamic programming approach reduces this complexity to O, n, by leveraging the grouping of numbers, efficient frequency computations, and state transitions. This dramatic improvement is what makes the dynamic programming solution scalable. Whether we're in the best case scenario, where minimal computation is needed, or the worst case with maximum distinct values in each group, the time complexity remains bounded at O, n, ensuring consistent performance across different types of inputs. Finally, let's solidify the reasoning behind the big O analysis of our algorithm. The frequency computation step is linear in n, which is O, n. The dynamic programming transitions dominate the computation with a complexity of O, k asterisk max underscore XOR asterisk m, which simplifies to O, n asterisk max underscore XOR, when accounting for the worst-case scenario of distinct values in each group. Adding these together gives a total time complexity of O, n, plus O, n asterisk max underscore XOR, which simplifies to O, n, since max underscore XOR is a constant value of 1024. On the space side, the frequency array contributes O, n, and the dp arrays add O, max underscore XOR, resulting in a total space complexity of O, n. This careful design ensures that the algorithm is both time and space efficient, making it well suited for large inputs and a clear improvement over exponential brute force methods. A common pitfall when solving this problem is misunderstanding the XOR property. Remember, XOR is both associative and commutative, which means the order of operations doesn't affect the result. If you fail to apply these properties correctly, your solution might become overly complex or even incorrect. For example, instead of simplifying XOR calculations, you might end up writing redundant code that doesn't take advantage of these fundamental properties. Another frequent mistake is improper segment division. It's not enough to just divide the array into k segments arbitrarily, each segment must meet the problem's constraints to ensure the XOR of all segments equals 0. If segments are divided incorrectly, the solution becomes infeasible. Lastly, relying on a brute force approach, where you try every possible way to divide the array and replace elements, is highly inefficient. This leads to exponential time complexity, which is impractical for larger inputs where n can go up to 10,000. Efficient solutions are crucial to handle constraints like these effectively. Another mistake to watch for is overlooking modulo operations when implementing dynamic programming. When using dp to manage XOR values, it's important to modulate indices by k to ensure proper alignment. Without this, your dp table might run into out-of-bounds errors or misaligned states, leading to incorrect results. Additionally, neglecting edge cases can cause issues. For instance, what happens if k is greater than n, or if all elements in the array are already 0? These scenarios can easily result in runtime errors or inaccurate outputs if not handled explicitly. Now, from an interview perspective, understanding this problem is a chance to showcase your grasp of XOR properties in dynamic programming. You'll want to highlight how XOR simplifies the problem space and demonstrate your ability to optimize solutions. Discuss the trade-offs between brute force and dynamic programming, and explain how pre-computing XOR values reduces redundant calculations. Be ready to address edge cases, and clearly articulate the time complexity of your approach. For example, in the optimized DP solution, the time complexity is n*2 to the power of k, and it's important to show you understand how this scales with larger inputs. This problem also connects to several related problems that leverage similar concepts. For instance, in LeetCode 1442, count triplets that can form two arrays of equal XOR. The focus is on XOR properties and the use of prefix XOR values to simplify calculations. Another example is LeetCode 1542, find longest awesome substring, which combines bitwise operations with state tracking for efficient solutions. If you've worked on LeetCode 1310, XOR queries of a subarray, you'll notice it also involves efficient range queries using prefix XOR. Lastly, while LeetCode 98, validate binary search tree, might seem unrelated because it doesn't involve XOR, it emphasizes the importance of segment validation logic, which is a transferable skill when working on this problem. Exploring these related problems can deepen your understanding of XOR operations and help you refine your approach to similar challenges. When considering alternative approaches to solving this problem, the brute force method is the most straightforward but also the least efficient. This approach involves trying all possible ways to divide the array into k segments and replacing elements to meet the XOR condition. While simple to understand, it quickly becomes infeasible for larger n due to its exponential time complexity. A more practical solution is to use dynamic programming. With an optimized DP approach, you can track the minimum changes needed to achieve each XOR value at every segment. This reduces the problem to a manageable n*2 to the power of k complexity, but it requires careful handling of state transitions to ensure accuracy. Another option is to use a greedy approach, where you make local optimal replacements to achieve the desired XOR value. However, the trade-off is that greedy methods may fail in cases where local optimality doesn't lead to a global solution. Each approach has its strengths and weaknesses, so it's important to choose the one that best fits the specific problem constraints and input size. Great work! To wrap up, we reviewed the problem, explored dynamic programming as our main approach, and discussed key takeaways like the importance of XOR operations and optimization techniques. Thanks for watching, and don't forget to subscribe for more coding tutorials. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!